And thank all the organizers for inviting me here. And of course, Carlos is completely right. This is a continuation of what Luis started presenting a couple of days ago. The idea is to consider, well, I have a recap of what Luis presented in his talk. So let's start from the recap so that it will be clear what the thing is going on. So we will still speak about this two-layer logic for uncertainty. In particular, we will focus on additive uncertainty. So in particular on probability measures. And let me recall what Luis presented in his talk about the logic FP-CL. So this logic has been introduced by Luis, of course, together with Peter Hayek and Francesco Esteva in '95. It has been called in several ways. I will use this notation today, FP-CL. FP stands for, sorry, fuzzy probabilistic, and C for classical logic, because we are interested, well, actually, what Luis presented is the version of the logic where events are expressed in terms of classical formulas. L instead stands for Lukasiewicz logic, because it is the outer logic that allows to reason and to express properties of probability measures. Now, remember that in this setting, the language we have is not an algebraic language in the sense that we have this extra operator P that stands for probably, or it is probable that, and it cannot occur nested, and there is another constraint in the sense that modal and non-modal formulas cannot be, there is no interaction between these two kind of formulas. So if we have, for instance, two classical formula, psi and phi, which express events, in this setting, psi implies P of phi, for instance, is not a formula, and P cannot occur nested. So P of phi implies P of psi is not a formula either. So, in other words, the formulas we are interested in are just Lukasiewicz formulas or Lukasiewicz terms, MV terms, let's say, on variables that are expressed, that are expressing the probability of classical events. So whenever you have k classical events, psi1, psi k, and you add and you put the probability operator in front of them, then you can close under the operations of Lukasiewicz logic. And those are, in fact, the formulas that we are dealing with. Maybe you can think it is a quite poor language, but in fact, it is enough for expressing all the properties of probability measures. In fact, the axioms that Luis presented are these three axioms together with the necessitation rule, in particular, the axiom A3 that express the finite additivity law of probability functions. So this is the syntax, those are the axioms, and models are, of course, probability measures. Luis presented models in a quite different way, but the key point in every model is that you have, in fact, a finitely additive probability measure that allows to evaluate basic model formulas. So the formula P phi in a model mu is evaluated in terms of the probability of the set of models of your classical formula phi. This is the very basic idea. If you have a compound formula that we will write in this way, it's just a term T that applies on these atomic model formulas that act as variables, then you just use the truth functionality of Lukasiewicz logic to compute the truth value of the compound formula phi. Of course, Lukasiewicz logic is truth functional, probability logic are not truth functional, but since Lukasiewicz logic acts outside of the probability operators, it is truth functional. So the whole logic is not, but the outside part of the logic is truth functional. And what Luis, Peter Hayek and Francesco Esteva proved is that, in fact, the logic is sound and complete with respect to probability measures, so these probability models. Now, I want to show you a picture that show, in a certain sense, which is the usual strategy to prove completeness for this logic. The usual way, if you remember Luis' talk, is to translate the modal part of this logic, so starting from the modal formulas P phi, to the propositional language of Lukasiewicz logic. So whenever the usual strategy for proving completeness is to start with a formula phi, a compound formula that is not a theorem of our logic FP, and then we start translating it The first translation, this is just much more an historical remark rather than a technical thing, but let me explain it in some details. So whenever you have a formula that is not a theorem, what you do, you take a translation of the modal part of your logic, so the probability part of the logic, and you translate it at the level of propositional Lukasiewicz logic. So the formula phi translates into this phi bullet, and all the axioms and the necessitation rule are translated as well, and they give rise to a theory that is called here FP bullet. And if phi is not a theorem, then phi bullet cannot be deduced from FP bullet in Lukasiewicz logic, in the propositional Lukasiewicz logic. Now, the problem is that when you translate all the possible instances of the axioms for the modality P, the theory FP bullet is infinite. And then you cannot pass through the completeness theorem of Lukasiewicz logic, the standard completeness Lukasiewicz logic, because Lukasiewicz logic is not strong, complete with respect to deduction from infinite theories. However, you can adapt a further translation of it, and essentially this further translation is concerns with considering, instead of all the possible instances of all formulas that you can write in classical logic, you just take them up to logical equivalence, right? So since we start with a finite language, there are only finitely many classical formulas up to logical equivalence. So this further translation actually converts the FP bullet in another theory, FP box, that is finite, okay? So the fact that phi is not a theorem translates in Lukasiewicz language by the fact that the theory FP box, which is finite, does not prove phi box. And then, yes, you can use the completeness, the standard completeness of Lukasiewicz logic with respect to the real unit, the algebra, the standard algebra on the real unit interval 0, 1, to find a model V, so evaluation that makes FP box true, but it makes phi box false, okay? Now, since V satisfies all the axioms of P, so it is indeed a probability measure. It's not just a logical evaluation. Actually, it is a finitely active probability measures. And this gives you, finally, the counter model of phi at the level of the logic FP. I used to call it the U-shaped proof because you start here, then you go down, you pass through the completeness theorem, and you go up to finding a probabilistic counter model of your formula. Okay, we will see that this strategy doesn't work always. In fact, it doesn't work when you want to extend your logic to have more complex events, let's say. So for the classical case, and indeed, whenever the logic for your events is locally finite, everything works because of the last translation gives you a finite theory. But in general, when your logic is not locally finite, as in the case of Lukasiewicz logic, this strategy for the proof does not apply. So we have to invent another way to prove standard completeness. So I will focus today on the logic FP double L, in which, in fact, we just replace classical logic for events with Lukasiewicz logic. The axioms, if you focus on the axiom for the new modality P, they are more or less the same as we showed before for classical events. The unique difference, of course, is the axiom A3, because if probability measures are the way to quantify uncertainty on classical events, when you move to non-classical events, you don't have in principle probability measures. You have this other notion of for the uncertain quantification that are called states of MV algebras. So states of MV algebras were introduced by Daniele Mundici in 1995, and those are maps from any MV algebra A to 0, 1, which are normalized and finitely additive. Of course, here the finite additivity is expressed in terms of not the lattice operation of MV algebras, but in terms of the monoidal operation. So whenever A and B are disjoint in Lukasiewicz terms, so the product of A and B is 0, then the state of the sum of these two events is the sum of the states. So the finitely additive version in MV terms. And this is the reason why the axiom A3 takes this shape here. Okay, is expressed in terms of the monoidal operation rather than the lattice operation of the logic. We have to say that the idea of using this two-layer logic have been used quite a lot in the last years. In particular, there are several work in this direction provided by, made by, for instance, I think of Enrico Marchioni, who started working also with me and Luis in this topic, but also Paolo Baldi, Peter Cintula, Carlos Noguera. And in the last years, also Sabine Frittella and Marta Vilkova start adopting this general strategy to, for instance, to define very general uncertainty measures on non-classical logic for events, okay? So what is our intended semantics for a logic? The intended and standard semantic for our logic is just made in terms of state. So what we want is complete, and when we interpret the basic modal formulas as the state of the set of our formulas. So a state model will be just a state on the free MV algebra and generated, let's say, because we want, maybe we can start with a finite language to start with. The interpretation of model of formulas is exactly as in the case of classical events. The unique modification is that, of course, if psi, for instance, is a Lukasiewicz formula, the interpretation in the free algebra is made in terms of what are called McNaughton functions rather than Boolean functions. McNaughton functions are, let's say, the functional representation of formulas in Lukasiewicz setting. And those are continuous function, piecewise linear with integer coefficient, and real valued. So a real valued continuous function, right? A particular class of real valued continuous functions. And whenever events are interpreted in terms of these functions, the evaluation of a probability of this event will be the state of that McNaughton function. And compound formulas as before, they are computed by truth functionality here. Now, let me skip these two parts here because I will have a picture that I hope will explain this better. So the first attempt we had to prove completeness for the logic with respect to state models was to use the U-shaped strategy for the proof. We start from a formula that is not a theorem of the logic FP, now FP double L, of course. Then we start the first translation, and it gives rise, of course, to an infinite theory, FP bullet. And then we try to translate it once again in order to make it finite. But of course, Lukasiewicz logic is not locally finite, so it doesn't give rise to a finite theory. So we cannot pass through the finite strong standard completeness of Lukasiewicz logic to find a counter model for the formula phi box. However, Lukasiewicz logic is strong complete, but not with respect to reals. It's strongly complete with respect to hyperreal numbers. So if you take ultra product of the standard MV algebra MV, then you can recover somehow the strong completeness of Lukasiewicz. So you can allow actually deduction from countable infinite theories. So let me explain this again by this picture here. So once you have a formula, a compound formula in the probability logic that is not a theorem, you translate once, you translate twice. Again, this FP box is not finite, it's an infinite theory. But then the strong non-standard completeness can be applied. Okay, so you can find a evaluation in a hyperreal based MV algebra that is a model of FP box, but which is not a model of phi. So this is the counter model that you can find in this case. What this V star is it a state? Well, no, it's not really a state because states are real valued functions. So those are hyperstates. So are states in the sense they satisfy the same equation, they are normalized and finitely additive, but they take value in ultra power of 0, 1, and d. Okay. So it is not modulo the strong completeness of the strong non-standard completeness of Lukasiewicz logic is not difficult to see that the probability logic is complete with respect to hyperstate models, but we want the standard completeness. And in order to prove standard completeness, we have, as I said before, completely changed the strategy for proving it. The U-shaped strategy for the proof doesn't work. I will go quite fast here because details are contained in the paper that is cited at the end of this presentation. But let me just give you a hint on how to prove it. So we have our formula, file is expressed in terms of these atomic formulas, p psi 1, p psi k, those are interpreted in the free MV algebra as Macnaghton function m psi 1, m psi 2, etc. So we have hyperstate completeness. So there is a hyperstate that takes hyperreal values and which witness the fact that the formula is not true here. And the hyperstates, if applied to these finitely many formulas, gives rise to a finite subset of this MV chain, okay? Now, every MV chain partially embed into the reals. So what it means that this finite set can be actually partially embedded into the real numbers, so in the standard MV algebra, and this gives rise to this map as tau, which is a partial map, right? It's a partial map from the free algebra to 0, 1. So then the question is, does this map extend to a state? Because it is not a state, we want a state. It's just a partial function. Now, there are two ways to prove that this extends. Well, two possible ideas occurred in order to see if this map actually extends to a state on the free algebra. The first one is try to encode the fact that it is indeed a state, it's a complete state. But algebraically speaking, this gives rise again to an infinite subset of the hyperreals. And this cannot be partially embedded. This is the algebraic version of the fact that you don't have a strong completeness of Lukasiewicz logic. However, there is another way to encode the fact that what you want is a state, and this encoding is finite, is using distributions. And the idea is the following. Whenever you have events like these two, for instance, you have two Macnaghton functions, the yellow one and the white one, you can just look at the finitely many points in which these functions are not differentiable. Believe me or not, this is enough to define a state on the whole algebra, considering not the state itself, but the distribution that is obtained by restricting the state of this partial map only to these finitely many points, okay? So the idea is, this is a pictorial representation of this idea. When you have a Macnaghton function here, you take only the finitely many points that are below it and that rebuild this Macnaghton function in some sense. Then when you apply the hyperstate to not just to the Macnaghton function here, but also to this point that are below, you get here a hyperreal value distribution that allows you to rebuild this value here, right? Essentially by taking the sum. It's like in Boolean algebras when you characterize probability functions in terms of distributions on the atoms. MV algebra doesn't have atoms, but this kind of points make the job, okay? Those are still a finite subset of the hyperreals. Maybe it's much bigger than the previous one. In fact, it is much bigger, but still is finite. So again, it can be partially embedded into the reals, and this gives rise to a finite distribution, real value distribution on real numbers that in fact allows you to build a state that is a countermodel of the formula you want to disprove, that you disprove in the logic. So this is a very general idea for the proof. So there is no way to use the U-shaped proof as before. We have to, in some sense, use specific properties of states and of MV algebras or free MV algebras to prove standard completeness. If you don't like states because you think that they are exotic things, fear not, because states, the idea is that if you look at formulas of Lukasiewicz logic as continuous function, you can think about them as continuous and bounded random variables, for instance, in probabilistic terms. And in fact, it turns out by what Daniele recalled a couple of days ago, the Krupa-Panti theorem, that every state is nothing else than the integral of the function that is represented by, that represents your event, is the integral of this function with respect to a unique regular Borel measure on the compact Hausdorff space of maximal filters of the MV algebra you start with. So states, in some sense, are a very classical notion, are just the expected value of some specific, continuous, and bounded random variable. So since we have completeness with respect to states, it's quite trivial to have completeness with respect to models that resembles classical measure. I have 10 minutes.
Yeah, now you have 9 minutes left.
So
just to let you know.
Okay.
Yeah.
Okay, good. So if you think about states as a non-classical notion in some sense, Borel models are very classical kind of models because they are just made of a compact Hausdorff space. You have, of course, a Lukasiewicz evaluation to interpreting your formulas in terms of function, but function is just a continuous function. And then you have a regular Borel measure on X called mu, okay? How to interpret now formulas in this kind of models? Well, it's trivial because previously we were interpreting P of phi in the state of phi. And here we just, since the state is the integral of that function, we just interpret the formula P phi in the integral of the function associated to it given by the Borel measure that is attached to the model we are considering. And compound formulas are defined in a similar way. And well, this is not really exciting. The logic, of course, is complete. I mean, here we are just representing state in another way. I mean, there is nothing really exciting behind this result. But what is interesting is that using Borel models, we can prove that the logic FP double L has the finite model property, and finite in a very quite strong sense. Because for a Borel model, so we have a set here evaluation and a Borel measure, a regular Borel measure mu. We call it finite if the supporting set, the set of, let's say, of possible words is a finite set. But the evaluation of propositional Lukasiewicz formulas just takes value in a finite chain. And also the measure is finite in a quite strong sense, in the sense that the measure is just a finite density function on the finite set X, and it takes value only in a finite MV chain. Okay, so the probability values, the starting probability values can just belong to a specific and finite range. Okay, and still the logic is sound and complete with respect to this class of models. So the finite model property, usually when we think about model logic or also in measure theory, we just restrict our domain to be a finite set of points, right? But a model of this kind is finite in the sense it really has a finite encoding, right? Everything that appears in a finite model can be encoded in a finite in a finitary way. So summing up, we saw models for this logic starting from the more exotic ones, so hyperstate models. Then we show this standard completeness and then state models, Borel models, and finite Borel models. Well, all these models share the same tautologies. Okay, they just share the same formulas that are true in each of them. So just to conclude, I want to spend just a couple of minutes maybe on the future work on this setting, because this is the first point is related to something that I think Paolo Agliano asked to Luis a couple of days ago, because he said, well, this logic is not algebraizable. Well, in fact, these kind of logics are not in the usual sense, in the sense that there is not a variety of algebras, a quasi-variety of algebras that is the equivalent algebraic semantics for this logic. Maybe they are algebraizable in other ways, in other more general sense. However, with Sara, we proposed quite recently a class of MV algebras that actually are a subclass of projective MV algebras that are some of the algebraic models for this logic. So this logic, although they're usually interpreted in terms of Kripke-like models or states or whatever, they can in fact be interpreted just in algebraic terms, not in the sense of algebraizable logic, of course, but there is a way to interpret them in algebras, and you have completeness with respect to them. This is contained in a paper that we submitted. It is really submitted 2022, but in fact it's submitted to 2021 we have no idea where the paper is. So we hope we will receive some answer in the next days. The second point is related to what actually Carlos asked to Luis. I mean, what happens if we drop the delimitation of for the operator P, right? Can we have a logic in which the operator can be nested or can interact with the non-modal formulas? Well, this is of course possible, and the logic is called has been called SFP for strong FP double L. In fact, this logic is algebraizable. It has an equivalent algebraic semantics that is made in terms of MV algebras with an internal state. We introduced this logic with Franco Montagna in 2009. This is the good news. The bad news is that we know nothing about standard completeness for this logic. I mean, the first hope was to try to apply the strategy I present to you today to this more general case, but it is more or less 1 year that we are trying to prove standard completeness for this logic with Sara and also with Serafina Lapenta, and we didn't succeed yet. I mean, it seems to be much more complicated than it appeared at the first stage. And finally, again, the U-shaped proof, this of translating and then applying completeness at the propositional level, have been used several times to prove completeness, standard completeness for this kind of logics. It doesn't work if your events are represented in terms of a logic that's not locally finite. So now we are trying to work on this to prove standard completeness for extension of this logic that maybe are more general than probabilistic logic. So logic, for instance, for belief functions, imprecise probability that Luis also presented 2 days ago. And we are progressing in this line with Esther Corsi, Eike Losny, Luis, of course, and many others. So let me just conclude with some references. The proof I try to present you today is contained in the reference number 2. So it is on standard completeness and fundamental property for probabilistic logic on Lukasiewicz events. And there you will find much richer bibliography that relates this setting to what I presented you. So thank you very much for your attention.